Okay, so here's the next question that we have on the menu today. It is asking us if there exists a perfect sphere with mass m and radius r, it is accelerated on a straight line towards the speed of light. If there is an instantaneous acceleration to, pretty much 99.999% of the speed of light, which is c, over a distance of l to a non-moving observer, what is the new r and the new mass of the particle while it traverses l? Okay, so this is what we're getting into. We are talking about relativistic effects. And this is very tightly associated with Albert Einstein. He's actually on that poster right there that I have of the Slovey conference. A bunch of very sharp physicists from all over the world gathered together to talk about big brain stuff. So this is associated with Einstein. He's a pretty smart guy, can't lie. And so, okay, so this is what we pretty much, the things that we want to keep track of. Okay, so in relativity, we have mass increases at high speeds we have lengths contract at high speeds and time slows at high speeds. Okay, and the amount that we have, the change in these parameters, we have the Lorentz factor. So Lorentz factor this is a factor of these above changes. So it's represented with the Greek letter gamma, which pretty much just looks like an upside down cursive L. And this is going to be, under the root, it's going to be 1 minus the velocity over the speed of light. Okay? So, those are both squared. V squared over c squared. Okay, so that's gamma. So, to a non-moving observer, things moving close to the speed of light are going to get smaller. Lengths contract. Okay, so if for us our v is equal to 0.999, how many nines do we have here? Triple nine. So we have 9 nines. C. Let's calculate our Lorentz factor, our gamma, and then we can much more easily have these equations over here. Otherwise, we're going to be rewriting the equation. So it's better to have like this term, because as you can see, this term is common to a lot of these things. Like if it also mentions stuff about time, we can calculate the time dilation with the same gamma. Yeah. So for our gamma in this situation, we will have 1 minus 0.999999999 c all squared. That's our v value, divided by c squared. So the c's cancel out, so effectively we just have 1 minus 0.999999999 squared. Okay, and let's send that to our calculator to figure out precisely what that is going to be. So under the root, 1 minus 0.9999999 squared is, our factor for here is going to be 4.47 times 10 to the negative 5. And the Lorentz factor will always be less than 1, or will always be 1 or less. always less than 1. Actually, instead of less than or equal to. The only way that it could possibly be 1 is if you have 0 velocity. Basically, you're sitting still. Okay, so given that we have our Lorentz factor here, we just got to multiply it together with our length. So the first part is asking us if there's what is the new r and the new mass. So the new r is just going to be r times this. So r new is going to be r original times gamma, which is just going to be 4 point r original multiplied by a term of 4.47 times 10 to the negative 5. Okay, so you are getting the radius is going to appear much shorter than it would otherwise. Okay, so radius as a length is going to contract, so becomes much smaller. Okay, so that would be our r. Now for our mass is going to get much bigger, and when we know that things are going to get bigger, they're going to divide by the Lorentz, by the gamma, and when things are going to get smaller, they're going to multiply by the Lorentz. And since we know that the Lorentz is always smaller or equal to 1, that always is going to be true. When you divide by something less than 1, you're always going to get a larger number, and when you multiply it, you're always going to get a smaller number, or equal. So here for the mass, our new mass is going to be our mass original divided by our Lorentz term. So this is going to be m original over 4.47 times 10 to the negative 5. And just to bring that on the upstairs to make this a little bit more easy to deal with, this is going to be equal to m nu is going to be the same as the original mass scaled by 22,361. Okay, so you are going to get significantly heavier when you move close to the speed of light, and this is part of the reason why no one has ever figured out a way to move faster than the speed of light, because you know, as you get heavier and heavier, it takes more and more energy to move you. So trying to move yourself at speeds like even kind of close to the speed of light is an extremely large engineering challenge that is pretty tough to solve. Can't lie. So yeah, this would be yeah, multiplied by 22,361. Cool. So the above solution here is good. Awesome. Thanks, Einstein.